In this short video, in today's class, we're gonna talk about two topics. One is called Gaussian discriminant analysis. Specifically, we're gonna talk about using two different decision functions. One is introduced by quadratic discriminant analysis, and another one is called linear discriminant analysis. Okay. So, but before we start, let's review about the Gaussian distribution or normal distribution. So because these two classifier requires the Gaussian distribution. So multivariate normal distribution. Normal distribution. Recall a random vector is said to follow normal multivariate normal distribution. You can think x is a random vector. For example, x could be x1. We have two features, and these two random variables jointly follows some normal distribution. So x follows a normal distribution with location parameter mu. Okay, so this has dimension d. So this average also has dimension d. And so here we assume they follows a common. So this is a scalar. So in today's class, we just assume this is a special case of the normal distribution where this covariance matrix is just a scalar. Each of the random variable they follows the same variance. Okay, if x has a density function, PDF, probability density function. So in the future class, we call it probability D represents density, F represents function. Okay, x has a PDF as following. So here, x is a vector equals to 1 over square root 2 pi sigma square to the power d. Okay, if we had two dimension features, then this d is 2. Exponential negative 2 sigma square. The numerator is the norm, the x vector minus the location vector, and the square. Okay. So here the average is a vector. The variance is a scalar. Okay, d is how many features do we have, and for each class C, suppose we know the parameter mu c and the sigma c square. Okay, so this will give us, for example, the probability density function. For example, among the cancer patients, what's the distribution of x? So you can think x here is calories. How much calories a patient intake every day. So this is a function of x vector. And with prior information. Prior means before we do the classification, we wanted to know in our population how much population is classified in this class C, or in our cancer example, how much population has this cancer. Okay, so here is one example. Let me put it up a little bit. For example, this is a bivariate PDF of the two-class normal distribution. Okay, and in this case, we have two features. So this is one feature x1, and this is another feature x2. So we have the bivariate normal two bivariate normal CDFs, and so here we have the one location. So suppose the first distribution is centered at mu C here. The second distribution is mu D. Okay, suppose we have two classes. So for example, C denotes a cancer. For example, the cancer class. And D denotes the not cancer, no cancer group. Okay, so we have two mu average, but here we assume the variance is denoted by sigma square C and sigma D square. Okay, and based on the Bayes theorem, the posterior distribution is proportional to the prior distribution. This is the prior, which means how much population has this cancer. And this is, you can think this is the data information we get from data, that based on the hospital's data history record, among the cancer patients, what's the distribution of the calorie intake? Okay, and this will give us the decision function. Okay. In today's lecture, we assume the features, the variance, we have a single variance. So we have the scalar variance. Okay, so variance x1 equals to the variance x2. So the variance among the two features has the same variance. Okay, therefore we can see the contour plot is a circle. Okay, if you don't have this condition restriction, then our contour plot looks like an ellipse. So we have elliptical distributions. But in today's lecture, for simplicity, we just assume they have the equal variance. And this is also called isotropic normal distribution. So it's called isotropic normal distribution. Isotropic normal distribution, and the variance will be the contour plot will be circles. Recall from our last lecture. Given some feature for new patient, given new data point. Give a sample point x. Okay, the Bayes decision rule. R star x predicts class C. Predicts the class C. That maximize f x given y. So this is a data distribution x multiply the prior distribution on the. So this is a scalar, this is scalar, right? So for each of the x, we can calculate, we can fit the normal distribution here. We can calculate this quantity, we calculate this quantity for each class, and then we pick the classifier predicts the class with the highest quantity, like this one. So this is our so in other words, base packed. So this is base base decision rule R star. Maybe I will use different ways here. Rx. Pick the class. With the biggest posterior probability. Okay, so that's the idea. That's the idea. That's what we, if you want to know more details, please check the video of last lecture. Okay, so actually today we're gonna use another notation. It's called, actually if you want to maximize this, we give a log transformation. You're gonna see this trick a lot in machine learning area, because usually this quantity may be small and this pi c is even smaller. So to make a numerical more feasible, computation more feasible, we usually commonly take the log. And actually, if you take a log of this function, we denote this as a q function, qcx, which equals to natural log, and by the x given y equal to c x multiply the pi c. Okay, so this equals to natural log of the f x given y equal to c x plus a constant log pi c. And actually this, we know what's the format of this, right? Format this by definition, the quantity is here. So by taking the log, we have the equals to, after getting rid of the constants, because constant 2 pi, square root 2 pi, we can get rid of 2 pi. So after simplify, and the natural log will cancel the exponential, we should get this one. So we get negative, I'll write down the top first part, the vector x minus mu c square 2 times sigma c square minus d times natural log sigma c plus natural log pi c. So this is ignore all constants irrelevant with c. With class C. Okay, so actually for each of the class, we can just calculate this quantity. Okay, so in two class problem, you just incorporate, you just calculate this QC, and pick the class with highest QC value. But this, I think this is we further assume we assume the symmetric loss. In other way, we assume the false positive and false negative has same amount of the loss. But if you do not want to have this assumption, probably you need to plus another loss function. Loss of -1, 1. But in today's class, we just assume, for simplicity, we just assume we use the symmetric loss. We use symmetric loss. Okay. Okay, so I'll continue in next video.